Okay, so this is a tutorial on Introduction to Radioactivity. We're going to start with the basic review of the nucleus, atomic number, atomic mass, neutron number, talk about the idea of stability and radioactivity, and then turn our attention to basic nuclear reactions involving alpha, beta, and gamma decay. Further tutorial will focus on half-life and binding energy graphs. Alright, so we've mentioned before in class the basics of a nucleus, right? The small, tiny core of an atom, and the way we symbolize it. So for this one, we have aluminum, we have 2713. The 27 is indicative of the mass, and the 13 is indicative of the atomic number. And so we give each of those a symbol, and we want to relate it to the number of protons and neutrons. So Z is the standard symbol for atomic number. Okay, and most important thing to remember is that's the number of protons in the nucleus, as well as the number of electrons for a neutral atom. So keep that in mind. A is the atomic mass, and that's given in atomic mass units, which is generally whole numbers for most of our purposes. Occasionally we'll have it down to a few decimals. And then a simple calculation you should be able to make is figure out the number of neutrons, which is the atomic mass minus the atomic number. Okay, so we'll see where that'll come in handy later on. So let's talk about the role of neutrons. You learn in chemistry that the number of protons are essentially the identity of the element, and that's how you move up or down through the periodic table. The neutrons are in the nucleus more than anything to act as a buffer. Okay, they're there to essentially offset the repulsive forces amongst all the protons that are crammed into a femtometer, 10 to the negative 15th meters. So as you cram more and more protons, higher to higher atomic numbers, you want as many, if not more, neutrons in there in order to offset that repulsion and allow the strong nuclear force to keep the nucleus more or less stable. Okay, so the neutrons help produce stability, even though they contribute to mass. Without them, you can't have a nucleus higher than 1, because you're not going to put two protons next to each other. Strong nuclear force just isn't enough. Alright, so we're going to spend a little bit of time with these two graphs, which are the same graphs, just slightly different details. Our focus is going to be on the stability of a nucleus. There are hundreds of different nuclei for the 100 or so atoms we find naturally. Okay, and not all of them are stable. So there's a nice little relationship that kind of gives you an idea of how the number of protons varies with the number of neutrons. So if we look at this graph, we can see a straight line where basically the slope is 1. The number of protons, Z, is equal to A minus Z, which is the number of neutrons. So we see that at very low atomic numbers, these numbers are more or less the same, but after around atomic number 20, we see that it deviates to a slope greater than 1, indicating that there are more neutrons than protons. Okay, so to summarize that first statement there, we see that first of all, for a given atomic number, which is along the x-axis, it's very hard to tell here, but there are multiple values along there. Alright, so this introduces the concept of something we should be familiar with, and that's isotopes. Isotopes have the same atomic number, just different atomic masses because of the varying number of neutrons. Chemical properties are identical, it's just that the masses are different, which leads to some differences, but primarily it goes towards stability. As mentioned a few seconds ago, low Z values, the number of protons, Z, equals the number of neutrons. Anything higher than that, then the number of neutrons starts growing, greater than Z. And if you do a real rough calculation at the ratio, let's say for 60-40 here, 60 neutrons for 40 protons, the ratio is 1.5. Okay, nothing special about that, but just like point out that in most nuclei, it stays around that 1.5 to 1 neutrons to protons. Okay, let's look at the second graph, which is telling us a similar thing. In the second graph, we see this dark line that runs all the way and ends abruptly right about here, which corresponds, oops, that's a very poor line. Let's erase that. Okay, Anyway, it corresponds to an atomic number right around 80. Alright, so these are isotopes within this island of isotopes that's surrounding this, the dark gray that's on your paper, of stable isotopes. Okay? And anything that's off that line is going to be unstable, or as we say, radioactive. And we'll look at later, isotopes to the left or right of the line are less stable, thus are radioactive. Let's erase that. Try to do it better. Okay, and we'll define radioactivity in a little bit. Alright, and like I was saying earlier, we'll see the importance of where you are relative to this line. So if there are too many, these are isotopes with too many, that's to the left of this, or too few to the right in here, neutrons. So the number of neutrons relative to the number of protons is very important, and certain ratios will give you more stable than others. And we'll look at that again more. And then important to understand is, like I said earlier, the line of stability ends abruptly right about there. All this little island of isotopes are therefore radioactive. And this starts at atomic number 82, which corresponds to lead, which is a very stable nucleus for at least one of its isotopes. Okay, and generally these are all radioactive, not because they have too many neutrons, but rather they have too many protons. In other words, it doesn't matter how many neutrons you put in a nucleus. There's just way too much Coulomb repulsion to make this stable indefinitely. Some of these are radioactive with short half-lives, and many have half-lives that are in the order of billions to tens of billions of years. So the key takeaway is anything above lead is naturally radioactive. And some of these elements we actually have to create in a lab, and then some can be stable for quite a long time, but they won't be found in nature. Okay, so let's look at radioactivity in a little more detail. So the key thing we're going to show you here is this chart, which has a lot of information, a lot of detail. Some of it you have to memorize, but it kind of makes sense. So let's define radioactivity, because it is very different than fission or fusion. Radioactivity is a spontaneous event. Okay, you don't need any outside influence. Okay, and it's a spontaneous emission of radiation, so there's various forms, from the nucleus. And as I said, nothing from the environment can affect it. It is independent of temperature, pressure, location, the phase of matter in a particular compound is. If a nucleus is unstable, it will decay on its own time, at its own rate. And that's actually very important for applications of it. In terms of radioactivity, historically, it was an accidental discovery by Henry Becquerel in the late 19th century. Basically, he noticed that an ore of uranium was developing photographic plates, and he ruled out any other influences, so he realized it is emitting something. And then many radioactive isotopes were subsequently isolated by the Curies, Marie and Pierre, okay, in the early 20th century. The key thing to understand about the radiation is it takes one of three forms: familiar alpha, beta, and gamma radiation. Okay, and you need to understand the differences amongst these, the different masses, their charges, their penetrating ability, etc. And this chart will help summarize this. So I'm going to zip through this fairly quickly, and then we'll do some practice problems. Okay, so the alpha particle we've mentioned before, especially with the Rutherford experiment. That is a helium nucleus, so we'll write it as an H42. Okay, and those two numbers are very important in a lot of problems. So we can see from this that a helium nucleus is 2 protons, mass of 4, so there are 2 neutrons. So it's a fairly heavy particle to be emitting. The charge of this is +2 because of the 2 protons. The mass down to 4 decimals is, as you can see right here. So when we start doing binding energy problems or energy released, we want to use this rather than just a 4. In other problems we're doing nuclear reactions, the 4 by itself is fine, and we'll see when that applies. Okay, the other two are maybe a little less familiar to us, but they're pretty straightforward. So there's a beta minus and beta plus. A beta particle is nothing more than an electron, okay, which has a mass of 0 and a charge of -1. Usually we write it as E -1, but to be consistent with this symbolism, I'll write it like this for now. So obviously it has a charge of -1, and for all intents and purposes, for most of these problems, its mass is 0. Okay, it's an electron that's emitted from a nucleus, even though there are no electrons there, and that's a process we'll talk more detail when we do standard model, is absolutely identical to an electron found in the surrounding the nucleus, which is the beta refers to its origin, which usually is from the nucleus, whereas an electron is surrounding the atom. A beta plus is an anti-electron or a positron. In other words, it's just an electron with a +1 charge. It is the antiparticle of an electron. And again, we'll talk about antiparticles greater, but it's for all intents and purposes identical, except for the charge. So no mass, but a charge of +1. And the gamma, we've talked before, is a photon. Okay, its charge is 0, as all photons are, and it literally has no mass, as we've discussed before. Okay, so important differences. So if we give you problems about some of these particles passing through magnetic fields, it's very important to understand that the alpha particle will deflect one way compared to the electron. Because of their relative masses, it won't deflect as much because it's heavier for a given speed than an electron, and of course these two will have the exact same trajectories except in opposite directions. So maybe we'll see some problems where magnetism comes in, and a photon, a gamma particle, will not be affected by magnetic fields at all. Right. Now generally there's a reason why a nucleus will either emit an alpha, beta, or a gamma radiation. This is a generalization. It usually holds, but it's not a hard, fast rule. You usually get alpha particles when you have too many protons in the nucleus. Okay, and in other words, alpha decay is associated with high Z nuclei. Generally, anything above lead. Nuclei with the lower mass than lead some do have alpha decay, but this is an important generalization. Beta, on the other hand, are when you have nuclei with too many neutrons relative to the protons. So if we go back to the graph we saw earlier, all right, it is these elements above here are generally going to be beta minus emitters. Okay, and then I'll talk about right here, those that are below the line or to the right of the line are going to be beta plus emitters. Okay, so in other words, these would have too few neutrons. Okay, and we'll get some reactions involve that. Then lastly, the gamma particle is given usually when a nucleus is in an excited state. Much like we can see atoms being in an excited state, you can have the nucleons in a nucleus. They are not bound, they're rigid, not able to move. They can go in different energy levels, nuclear energy levels. And so when you have an excited state and it drops back down to the ground state for that nucleus, then a gamma photon will be given off. And we'll see the consequences of that. Alright, next basic fact you should know is the relative penetrating power, and actually I'm going to try to split this in half. Okay, and we'll put a little subtopic here, stopped by. In other words, what does it take to stop these particles? Okay. These are all ionizing radiation. In other words, when they encounter a living cell or a metal, it will ionize them. It will knock electrons off the atoms, because we're going to see that the energies of these are in the order of mega electron volts, whereas the ionization energy of most valence electrons is on the order of just electron volts. So one particle can ionize thousands of atoms. Generally, alpha particles have very, very low penetrating ability. In other words, they're absorbed very, very readily. They can be stopped by paper. A single sheet of paper can absorb an alpha particle. So for a human, if you're exposed to an alpha source, it will just be stopped by the outer layer of your skin. It's fairly harmless unless it's in high doses. Alpha particles can be very dangerous if you ingest them, so they're inside, so it doesn't matter how far they go, they're still going to do damage to cells. Beta, on beta positive or negative, doesn't matter because they're essentially the same thing, would be moderate. So they can be stopped by a, let's say, a thin foil of some sorts, usually, let's say, aluminum, some low Z foil. And gamma has very high penetrating ability. Okay, this is where you need lead to stop gamma rays. From a Superman has X-ray vision, can be stopped by lead. There's some truth to that. Not that Superman has X-ray vision, but that X-rays can be stopped by it. Same with gamma rays. But these tend to be the most dangerous externally. Okay, you have got a gamma ray source on your skin. It can cause radiation sickness, radiation poisoning, certainly mutations, cancer, etc. These are usually more dangerous internal, especially from a low activity source. Any acute amount of any of these can be dangerous externally, but internally these are more dangerous. All right, lastly, we're going to look at nuclear reactions involving each of them. So this next to last line here is just the general way of what happens when we take a parent nucleus, spits out an alpha particle, what changes about the daughter nucleus. Examples will clarify this, but it's pretty straightforward. Your mass drops by 4, your atomic number drops by 2. With the beta positive or negative, it's slightly more subtle. Again, our parent nucleus will change, but if we want to conserve charge, which is, or conserve nucleon number, if we emit a negative, then our charge has to go up by 1, such that Z plus 1 plus negative 1 still gives us Z. In other words, the element will go up in atomic number, yet the mass will not change, because the electron, for all intents and purposes, has 0 mass. Also, there is a third particle called the neutrino. In this case, it's an anti-neutrino, which essentially has no mass and no charge, but must be there for other conservation reasons, which we'll talk about at another time. And for a beta plus, it's the exact same thing, except that the atomic number will go down by 1 to conserve charge. Mass stays the same, and instead of an anti-neutrino, we get a neutrino. Lastly, and this is a little hard to see with gamma radiation, basically you start off with an element, you have the same element, just with a gamma. In other words, it's just de-excited, and so there's no change in mass or charge, so it's the same element, just in a lower energy state. So the classic example, or one example of this, is radon-226. We'll drop down to helium. That's your alpha particle, so the atomic number goes from 226, atomic mass goes from 226 minus 4 to 222. The number drops from 88 to 86 because of this, so they have to add up. And then there's extra kinetic energy. And for a beta negative emission, carbon-14, generally these are low Z, are the beta emitters. These are high Z. So we have a negative 1 there, plus 7 gives us 6, and 14 plus 0 gives us 14, and then we have an anti-neutrino plus kinetic energy. And then the way we generally show a nucleus that's excited is with a star or an asterisk, and so nothing's changed about it except that we've given off some energy, much like we do with excited electrons. Okay, so let's turn our attention to some practice problems. Alright, so some of the easier problems you'll have to do are basically balancing nuclear reactions, where the primary conservation law is conservation of nucleon number. In other words, you got to have the same number of protons you started with as with what you end, and the same number of protons and neutrons that you started with versus what you end with. Protons can turn into neutrons, neutrons can turn into protons in ways we'll talk about later, but that's basically the idea here. So here we want to fill in a missing blank and label the type of decay. So we start off with a calcium 4520, and we see that this is a beta emission, so we can recognize that from the electron, beta negative, or probably easier put beta negative. So very simple, we want 21 here, 45 here. You don't have to memorize the symbols, which element is atomic 21. I believe that is scandium, okay, but for what's important is the 45 and 21. And I didn't have the equation editor, but that would be nu is the symbol for neutrino, nu bar. We have to have an anti-neutrino when we have an electron. Alright, so here we have copper, and then we have a gamma, so that's clearly gamma emission. And since gamma has no charge and no mass, nothing's going to change, so it's still going to be copper 5829. Alright, here we have chromium to vanadium, something, and a neutrino. The neutrino is a clue that it's going to be a beta. Looking at the numbers here, 23 to 24, so this is going to be positive 1, 46, pen is not behaving, and this will drop down. Oh, excuse me, this is just, okay, that was a mistake. That's 0. Okay, so this is a positron, and so this is a beta plus emitter. And lastly, we have plutonium, gives off an alpha particle, so that speaks for itself, and we can work out the math. Pretty straightforward, 92. Since this is basically He 2 and 4, boy, this pen does not like small script. This is going to be 92, 230, and element 92, you probably should remember, it's not hard, is uranium. Okay, so that's fairly standard. I might introduce you, talking in class about electron capture, which would be essentially the exact opposite of a beta emission. Sometimes the nucleus would change by actually capturing an electron, and a proton will turn into a neutron, but we don't have an example right here. Okay, another one we want to be able to do is figure out how much energy is given off for a particular decay, especially in alpha decay. So we have uranium-232 decays into thorium-228 and an alpha particle. We want to know how much energy is released. And this is very similar to problems we did before. We want to figure out delta M, which is basically equal to the mass of the uranium minus the sum of the products. Since my writing is not very good, I'm not going to write in the actual numbers in there. You can work that out for yourself. Plus mass of the alpha. Okay, so this is in the table on the other page. When we work it out, we see that delta M is 0.0058 U's. Okay, and then we can use that conversion factor where the energy is going to be equal to the loss in mass times 931 MeV per U, and punch that in, and we get 5.4 MeV. So that's a fairly energetic process. It's not quite as much as a fusion reaction or even fission, but like I said, those are much greater, thousands of times greater than the ionization energy of most atoms, so they can do damage, especially in biological systems. Now the question is, where does the energy, how does the energy manifest itself? Okay, so we have two daughter products in this decay. We have the thorium, which is a large nucleus, and an alpha particle, which is a very small nucleus. As per discussion we had in class, the easiest way to approach this is looking at conservation of momentum to give us an idea of the relative kinetic energies. So in other words, if the parent nucleus is initially not moving for all intents and purposes, then the momentum is 0. So we can say that after the decay, the P of the thorium must equal the negative value of the P of the alpha particle. Therefore, if we square both of them, we can say that P thorium squared equals P alpha squared. Now, why do I want to square that? Because we can relate directly momentum to kinetic energy. In other words, from mechanics, we know that kinetic energy is P squared all over 2m. So if I bring the m over there, what we basically have is the Ke times the thorium times the mass of the thorium, right? Again, bringing the mass over here, I can ignore the 2 because it's going to be common on both sides, has to equal the Ke of the alpha particle times the mass of the alpha particle. And if we're looking for the ratio of the kinetic energies, then we can say that the kinetic energy of the alpha relative to the thorium is going to be equal to the mass of the thorium divided by the mass of the alpha So the mass of the thorium is 228. We don't need the super precise value, divided by 4, and that is 57. Okay, or 57 to 1. So 57/58 of the kinetic energy is in the alpha. Alrighty? Very, very little is in the daughter product. Then the last question, which type of decay would one expect from a lithium-5 nucleus? Explain and write the nuclear reaction. I want you to try that one on your own, looking at the relative number of protons, neutrons, and at the graph, the first graph we saw in the front. So this concludes our introduction to radioactivity.